Good day, everyone. In this video, we are going to tackle about continuity of a function at a number. Let me start my presentation. For the definition of a function continuous at a number, the function f is said to be continuous at the number a if and only if the following three conditions are satisfied. And again, if it will not satisfy the three condition, then we cannot say that a function f is continuous. We have here the first condition. F of a exists. And for the second one, the limit of f of x as x approaches a also exists. And for the third condition, the limit of f of x as x approaches a is equal to f of a. If one or more of these three conditions fails to hold at a, the function f is said to be discontinuous at a. And let's try to evaluate some examples. For the first example, let f be defined by f of x, which is equal to 2x plus 3 if x is not equal to 1, and f of x is equal to 2 if x is equal to 1. Investigating the conditions, let's start with the first condition. F of 1 exists, which is equal to 2, as stated here in a piecewise function that our f of x is equal to 2 when x is equal to 1. Therefore, if we substitute our value of x to our f of x, that is f of 1, and that's equal to 2, as stated by the piecewise function. For the second condition, the limit of f of x as x approaches 1 is equal to 5. If you are wondering why is it equal to 5, it's all because we are using the first function, which is 2x plus 3. And as we substitute there the value 1, that's 2 times 1 plus 3, that is equal to 5 as we solve for the limit. And for the third condition, the limit of f of x as x approaches 1 is not equal to f of 1 because f of 1 is equal to 2, and then the limit of the function f of x as x approaches 1 is equal to 5. Conditions 1 and 2 are satisfied, but 3 is not. Therefore, it's discontinuous at 1. It is a removable discontinuity. Let's have another example. Let f be defined by f of x is equal to 1 over x minus 2. This is our given function. Let's now investigate the condition. Investigating the conditions, for the first one, f of 2 is not defined. Why? As we substitute a value 2 to our denominator or to our value of x, the denominator will turn into 0. And when our denominator is 0, it is undefined. The function will be undefined, and therefore f of 2 is not defined. Since condition 1 is not satisfied, f is discontinuous at 2. The discontinuity is essential because the limit of f of x as x approaches 2 does not exist. And that is how we simply conclude a certain example. Let's stop with the first condition as we investigate, and we can now conclude that a function or the discontinuity exists, and that is essential. And for this example, let g be defined by g of x is equal to 1 over x minus 2 if x is not equal to 2, and g of x is equal to 3 if x is equal to 2. Checking the conditions, let's start with the first condition. G of 2 is equal to 3. Okay, so we have the first condition, so this is checked. For the second condition, we find for the limit. Let's start with the limit from the left. So the limit of g of x as x approaches 2 from the left. And that is equal to the limit of 1 over x minus 2 as x approaches 2 from the left. That is negative infinity. And for the limit of g of x as x approaches 2 from the right, this is equal to the limit of 1 over x minus 2 as x approaches 2 from the right, and that's also equal to positive infinity. If you're asking why is it negative infinity, because it satisfies the property of an infinite limit. Same goes with this example. Because condition 2 is not satisfied, G is discontinuous at 2. The continuous is essential. We can say it's discontinuous as we find the limit from the left and from the right. They are not equal. Therefore, the limit does not exist in this example, or the limit of g of x does not exist. And therefore, the function itself is also discontinuous, and that is essential. The continuous is essential. This is just a typo error. Typo error, this is that discontinuous is essential. Let h be defined by h of x is equal to 3 plus x if x is less than or equal to 1. H of x is equal to 3 minus x if x is greater than 1. We read this one as x greater than 1. Investigating the conditions, let's have the first condition. H of 1 is equal to 4 because as you substitute there the value, that is 3 plus 1, and that's 4 when x is equal to 1 because it's greater than, it's less than or equal to 1. Again, the function here, if x is less than or equal to 1, we can substitute the x1 here to the first piecewise function. That's 3 plus x. Therefore, 3 plus 1 is 4. For the second one, we find the limit of this h of x from the left and from the right. Let's start from the left. From the left, we substitute now the value of the function h of x, which is 3 plus x, as x approaches 1 from from the left. Therefore, the limit of 3 plus x as x approaches 1 from the left is equal to 4. And how about from the right? The limit of h of x as x approaches 1 from the right, just simply the limit of 3 minus x. Because it's stated here, x should be greater than 1, therefore we use this function 3 minus x. Because 1 from the right are functions or values located at the right or on the right of the value 1. And that is equal to 2 because 3 minus the value of x, which is 1, is equal to 2 using substitution or direct substitution. So h is discontinuous at 1 because the limit of h of x as x approaches 1 does not exist. The discontinuity is essential. It is also called a jump discontinuity. As you can see here, why is it discontinuous? Because at condition 2, the limit is not equal from the left and from the right. We can only say that a limit exists if The value from the left and from the right is equal. Let's have the function defined by f of x is equal to the square root of x minus 2 all over x minus 4. For the solution, we compute the limit f of x as x approaches 4. If you will say, uh, maybe sir, the value 4 will make our function undefined, you should not conclude that way. As you can see, this one is a rational function. And when we rational function and at the same time we have a radical symbol, and therefore we can also say this is a radical function. We solve first for the limit of f of x as x approaches 4. Look at the numerator. The numerator contains a radical symbol. We can simplify the function itself by finding the conjugate of our numerator, and that is x square root of x plus 2. Therefore, we multiply square root of x plus 2 to both numerator and denominator, and then we simplify. As we multiply this expression, the square root of x minus 2 times the expression square root of x plus 2, that's equal to x minus 4. Copy the denominator, and as you can see in this form, x minus 4 here and x minus 4 on the denominator, this is just equal to 1. Therefore, the remaining expression will be the limit of 1 over this over the quantity of square root of x plus 2 as x approaches 4. And this is the time we can do direct substitution and we can determine whether a certain limit exists as we substitute 4 to our x, that's square root of 4 plus 2 on the denominator's part, and that's 1 over 4 because square root of 4 is 2 plus 2, that's 4 on the denominator. We have the new function defined by f of x is equal to the square root of x minus 2 all over x minus 4 if x is not equal to 4. But when it's equal to 4, our f of x is 1/4. Therefore, the function is continuous at 4. This time, you are going to answer a practice exercise on your own. We have two examples for you to answer. I'll be giving you an ample of time to answer this part. And that ends our discussion for illustrating examples for continuity of a function at a number. Thank you so much and have a good day.